Okay, let's take a look at the solutions of the practice problems 20 from 5.2 on the section on optimization. So number one here, we want to find two numbers whose sum is 50. So my two numbers are going to be x and y. And I want to write both a constraint and an optimizer. So the constraint is going to involve the number, and that's this one. The sum is 50. So for the constraint, we need the sum of those two numbers to be 50. So that means that x plus y, because that's what sum means, has to be equal to 50. And then I'm going to take this other piece where it says their product is a maximum. And the thing that I want to maximize is my optimizer. Right? I want to find the optimum value, in this case, the max of the product. And the product of those two numbers is x times y. And so now what I do is I go over here to my constraint and I solve this for one variable or the other. So let's solve for y. So let's make it 50 minus x, subtract the x from both sides. And then we're going to go over here and plug that in for the y. And that will make my product equal to x times 50 minus x. And that's 50x minus x squared. Now this is the optimizer. I'm trying to find a max here. So I want to take the derivative and set it equal to 0 to find a max. So 50 minus 2x. And I'm setting that equal to 0. And if I add the 2x to the other side and divide by 2, that gives me x equals 25. So that's my first number. Now I want to make sure that this is in fact a max. So let's use the second derivative test. And in that case, the second derivative is -2, and that's always negative. So it's concave down, and there's my local max. So that works out. Then what I want to do is take my x equals 25 back over to my constraint in order to figure out my y. So here we're going to have y equals 50 minus 25, and my y comes out to be 25. So the two numbers are 25 and 25. For number 2, we have a rectangular field is bounded on one side by a river. So I've got a river and I've got a rectangular field. That is going to be x by y. Now we're assuming that it's straight, although it doesn't look straight. So I'm going to have x, y, and y. And what we know is find the dimension of the field that will maximize the area if the fence has a total length of 32 feet. So the fence has a total length of 32 feet. So you're adding up the perimeter in this case, your constraint. Your constraint is always given by the number that you're given. So in this case, the 320 feet. And that's the fencing, so that's my black areas. So x plus 2y has to be 320. And I'm going to go ahead and solve that for x, because we know we're going to need that. And the optimizer, it says find the maximum area. So the area here is just x times y. And then we're going to go ahead and take our x over and plug that in. And that's going to give me that the area is 320 minus 2y times y, or 320 y minus 2y squared. And then I'm ready to go ahead and take the derivative to find my maximum area. So that derivative of the area would be 320 minus 4y, and we're setting that equal to 0. Add your y to the other side, divide by 4 gives you y equals 80 feet. Again, we're going to use the second derivative test, make sure that this is in fact a maximum area. So this is -4, which is negative, concave down, local max. So that checks out. Then we're going to go ahead and take our 80 over here and plug it back in. So you're going to have x equals 320 minus 2 times 80, which is 160, which is going to give you 160. And so to answer the question, the dimensions are 160 feet by 80 feet. Number 3. All right, consider the chemical reaction. A plus B gives you AB. We find that the reaction rate is given by this this function where 0 goes to the minimum of whatever a and b are. Here we know that the concentration of the AB and the minimum of AB denotes the minimum of the two values of A and B. Constants of A and B are concentrations of the reactants, A and B at the beginning of the reaction. All right, now they're going to tell us what K, A, and B are. So that's going to give me my reaction rate. So R of X is going to be 2 times 2 minus X times 5 minus X. Okay, and we know that 0 is less than or X, less than or equal to the minimum of A and B. Well, A is 2 and B is 5, so the minimum of those two would be 2. All right, so if we go ahead and multiply this out, let's see, that gives me 2x squared. The middle term is minus 5x and minus 2x. So that's minus 7x times 2 is minus 14x. And 5 times 2 is 10 times 2 is 20. Okay, so we get 2x squared minus 14x plus 20. We want to find the derivative here. That's 4x minus 14, set it equal to 0. And x is going to be 14 over 4, which is 7 over 2, which is 4.5. But notice that my x has to be between 0 and 2, and this is definitely not in that interval. So I have to throw that one out. So now, if I'm throwing out that critical point, that means that either this reaction rate is either increasing on 0 to 2 or it's decreasing on 0 to 2. So if we think about the interval from 0 to 2, and we think about a test point for x, let's pick 1, and I plug that into the first derivative. If you plug in 1, you get a negative value, which means that it's decreasing. If it's decreasing on that interval, where is your local max and your local min? Well, your local max is going to be over here at the top at x equals 0, and the min is going to be over here at the bottom at x equals 2. So local max at x equals 0 and a local min at x equals 2. So now what's the question asking? It says, find the concentration that maximizes the reaction rate. So to give the local max, that's this top information. So at x equals 0, reaction rate is a max. And that actually should kind of make sense, because when you think about a chemical reaction, at the beginning of the reaction is when you have the most reactants. And so they're going to react together very quickly. And as you go, as you turn A and B into the product of AB, you're going to have less A and B to react together. And so the reaction rate is going to be slower. So it's going to start out really fast and it's going to slow down over time. So it's fastest when x equals 0. So that kind of makes sense. So when you don't have a critical point, you're going to work with your endpoints. Here's another one that's similar with endpoints. So we're given the function w of p. So w of p is equal to, now they give us all of these numbers. So w11 is 0.7, so this is 0.7 p squared. Our w11 is 1, so you're going to have plus 2p times 1 minus p. And then w22 is 0.3, so 0.3 times 1 minus p quantity squared. And let's go ahead and just multiply this sucker out. This is a little bit annoying, so let's just do it. So we have 0.7 p squared, 2p minus 2p squared, plus 0.3 p squared minus 0.6 p plus 0.3. And let's see, altogether, that's going to give me, I have 0.7 and 0.3, so that's 1 p squared, minus 2p squared gives me negative p squared. I have 2p and negative 0.6p, so that's going to give me plus 1.4p. And I have plus 0.3. All right, and so and again, this is given on an interval 0 is less than or equal to p is less than or equal to 1. So let's go ahead and find our derivative. So w prime of p is negative 2p plus 1.4. Set that equal to 0. Subtract your 2p over and divide. That gives you p equals 0.7. Second derivative gives you negative 2, and that's concave down, so that's a local max. Okay, now, what's this asking us for? It says find the maximum of w of p if all of these things. So we're looking for the maximum of w, and we know that that's going to happen at p equals 0.7. So to find the maximum, we want to plug that in. So we want w of 0.7. So that's going to be negative 0.7 squared plus 1.4 times 0.7 plus 0.3. And this turns out to be negative 0.49. Let's see. 14 times 7 is 49 times 2, which is 98. So plus 0.98 plus 0.3. And that's going to give us 1.28 minus 0.49. So I'm subtracting half minus a 0.1. So 0.79, I believe. Yeah, that looks right. So 0.79 is what I'm looking for. And in context, W, let's see. The average fitness of the population. So the maximum fitness of the population is 0.79. And then lastly, number 5, the altitude attained by the model rocket t seconds into the flight is given by the following function. Find the maximum altitude of the rocket. So our equation's already given, so we can jump in and take our derivative. Remembering here that, oops, sorry. Whoa, sorry, I just jumped things quickly on you. Remembering that your first derivative when it comes to position is going to be your velocity, and the second derivative is the acceleration. It's going to get negative t squared plus 8t plus 20, and we're setting that equal to 0. So that's t squared minus 8t minus 20 equals 0. And let's see if we can factor that. I'm going negative 10, positive 2. So t minus 10, t plus 2. And that's going to give me t equals 10 and t equals negative 2. And I'm going to throw out the negative 2 because we're not talking about negative time here. And so that means the maximum altitude should happen at t equals 10. Let's verify that it does using the second derivative test. So negative 2t plus 8. And when you plug in 10, you get negative 20 plus 8. So it's negative, concave down, and there's your local max we're looking for. All right, and so it's asked, says find the maximum altitude. So it wants a value for height when t equals 10. So we just want h at 10. And that is negative 1/3 times 10 cubed plus 400 plus 200 plus 2. So this is negative 1,000 over 3 plus 602, whatever that turns out to be. Well, 1,000 divided by 3 is going to be 333, so this is 602 minus 333.3. Let's see. So 67, 68, 69. So 269.6, I think, is what we're looking at, is our altitude. And do they give us units here? They don't. So it's in whatever units are given. So the height, or the max height, is 269.6.